Okay, hi everyone. So today we will start our look at the history of astronomy and we'll look at some of the big names and big contributions to the field. We will cover 6 astronomers from history in this class. They're on the screen here: Ptolemy, Copernicus, Tycho, Kepler, Galileo, and Newton. We will get up through Kepler in this lecture today. So as part of this class, you are required to complete a short paper on an astronomer from history and their contributions. You are not allowed to choose one of these 6 astronomers for your paper. You must choose a different astronomer, and I promise there are plenty to choose from. Astronomy has been practiced all over the world by all different kinds of people for thousands of years. There are many other astronomers and space scientists to choose from. And if you hand in your topic proposal and it uses one of these astronomers, I will give it back to you and tell you to try again. So not allowed to use these, but we will go over these 6 in class. Okay, so back in, ye olde times, astronomers really had 2 main goals: to explain or predict the movements and positions of the Earth, the Moon, the Sun, the planets, and the celestial sphere, and explain how all of those things relate to each other and to Earth. So this was really difficult to do because there were a couple of observations or lack of observations that were seemingly incompatible. So the first of these observations is retrograde motion. So retrograde motion basically means that something is moving in the opposite direction as most of the other things around it. So this is a picture, I believe, of Jupiter over the course of a few weeks as it moves along the sky. See, it moves along the sky, backtracks, and then goes back in the original direction. So retrograde motion in planets is an illusion caused by the fact that other planets don't orbit the sun at the same speed as the Earth does. We see this effect with planets closer to the sun than Earth and planets further away from the sun than Earth. A planet will go into retrograde when either the Earth overtakes the planet in its orbit or the Earth is overtaken. So there's this video of Mars when it was in retrograde in 2020. Let's see if it will play here. So the blue dot before I start it, this is Earth, and the red dot is Mars. At the top of this video is how the orbit looks from the top down. So here's the sun, Earth, and Mars. Uh, this box here is how Mars looks from Earth. So the Earth goes around the sun faster than Mars does. Let's see if I can get this to play. So we're going to see Earth overtake Mars and how that appears to change Mars's trajectory. So we're about to hit retrograde right now. See, as the Earth overtakes Mars, looks to change direction a couple of times. So this example is for Mars, but this happens when we overtake Jupiter and Saturn in their orbits, and it happens when Venus and Mercury overtake Earth. So even hundreds of years ago, before we had a better grasp of kind of what's going on up there, the fact that we saw retrograde motion of planets implied that Earth was moving as well. This didn't jive, though, with a second observation, which was a lack of parallax. So parallax is an apparent shift in position. So in this case, we're talking about stellar parallax, which is an apparent shift in the location of a foreground object against a background of stars. So this is a diagram of kind of how it works. We use the orbit of Earth. Maybe we make a measurement of this star in June. We follow this line. That star may look like it's over here, but when we make that same observation in December, it'll look like that star is over here. So parallax takes advantage of some well-known features of trigonometry and of Earth's movement through space to measure distance of relatively nearby objects. And here's kind of a more down-to-earth example of how it works. So let's say, for example, that you are riding your bike down a straight bicycle path, and in the distance, you see a beautiful tree standing alone in a field with a mountain in the distance. So here is that beautiful tree, here's the beautiful mountain. You notice at first that the tree is to the right of the mountain. So like, this is your point of view. As you're coming on your bicycle from this direction, you see this point of view, the tree kind of at the right. As you ride on, your perspective of the scene will change. So now your point of view is you are directly in front of both the tree and the mountain, and your point of view looks more like this yellow box right here. The tree and the mountain kind of are aligned. And now you've ridden on even further and your perspective changes again. So now you are over here and your perspective looks more like this box here. The tree looks like it's more to the left of the mountain than before. You've probably noticed this phenomenon before, right? Driving down the highway, things close to the road look like they're going by extremely fast, whereas things far away move much more slowly or maybe not at all. So this is what happens with parallax. So just replace the tree with maybe a nearby star or a planet, and the mountain with a stationary background of stars far enough away that they don't seem like they're moving. So the background stars, like the mountain, they're just very far away. They don't seem to be moving, and the close by thing, the planet or the close by star, will seem to shift position. Okay, so how does this movement actually help us find distance? So this is where trigonometry comes in. We can make a triangle and measure two very important quantities. So if you wanted to calculate how far away the tree is, all we need to do is measure this baseline length, right? The length of when you first made your measurement of the tree to when you last made your measurement of the tree, and a parallax angle, which is sometimes this entire angle, sometimes it's half of this. But it's the angle kind of up here between these two lines. So these quantities can be directly measured and used to calculate the actual distance to the tree. So we can use this with stars, but the problem is that this shift, when we talk about stellar parallax, so distance to planets and stars, is the shift is very tiny. And astronomers during this time simply didn't see a shift. We expect to see a shift if the Earth is moving. So the Earth is like you on the bicycle riding past the tree and the mountain. And since we don't see a parallax, it must mean that the Earth is not moving. So we have retrograde motion, which implies the Earth does move, but we don't see parallax, which implies that the Earth is not moving. So any model of the solar system or the universe needed to account not just for the movements of the sun, the moon, the planets, and the celestial sphere, but it also had to account for our observations of retrograde motion and our lack of observation for parallax. So this is not an easy proposition. So philosophically, at the time, it made a lot of sense to people that the Earth was the center of the universe. So the fact that we didn't see parallax didn't bother most people. So if you accepted that, then really what you needed to figure out was how to explain away retrograde motion. Okay, so let's start our tour of historical astronomy then with Ptolemy. So he lived circa 100 CE. He used a model of the universe called the geocentric model. Geocentric meaning Earth-centered. In this view, Earth was not only the center of the solar system, but the center of the entire universe. Ptolemy didn't come up with this model, but it had been espoused by Greek philosophers before him. And so basically, you had the Earth at the center, absolutely everything else, including the celestial sphere, kind of rotating around the Earth. Ptolemy really wanted to solve for retrograde motion. He wanted to make tables and predictions for the movements and locations of planets, and he really had to solve for this retrograde motion to do that. He explained retrograde motion with what are known as epicycles, or kind of circles within circles. So it's a simple diagram at the bottom here. So the idea is, to explain retrograde motion, the planets, the sun, everything orbits the Earth. So it goes around here, but it also travels in a little circle of its own. So it kind of goes like this around the Earth. Makes kind of a curly Q type of motion. So the entire time the planet is traveling around the Earth, it's traveling in its own little circle. So ultimately, this is an incredibly complicated system, as you can see here. If everything has its own little epicycle, we have all of these little curly Q overlapping motions. But that's what was used to explain retrograde motion. So we needed to do to keep Earth at the center of the universe. So people liked this, right? It fit with this philosophy that Earth is special, and it worked okay. Ptolemy published what are called his handy tables, which is literally what they are called. And those could be used to predict when and where planets could be observed within a few weeks, which was not bad at the time. So he explained retrograde motion by invoking these epicycles, and it really became ingrained, whether he meant for it or not. Circles kind of came to be considered like the perfect shape. So the heavens should also move in these perfect circles. Ptolemy was also responsible for the system of 48 constellations, as well as for the stellar magnitude scale, which astronomers still use today with some modifications. I've talked a little about those in previous lectures, so I won't go into detail about it now, but those were Ptolemy's other contributions to astronomy. The next contributor I'll talk about is Nicholas Copernicus. So he was a monk who lived in the 14 and 1500s, and he suggested a different model for the universe from Ptolemy. Copernicus suggested a heliocentric or sun-centered universe, not just the solar system, but the universe. The celestial sphere is kind of the outer circle, right? Still with this idea of perfect circles, like everything orbited the sun in a perfect circle. Copernicus also added that distances are actually much larger than we previously thought. So his universe was much bigger than the universe of Ptolemy. The tables Copernicus calculated were much better at predicting the location of Mars and other objects in the sky. I mean, go figure, he's at least orbiting the sun. So he could explain away retrograde motion by the fact that sometimes Earth overtakes Mars, like I showed earlier in that animation, which is a much simpler explanation than Ptolemy's epicycles. Just because it worked better and was simpler doesn't mean it wasn't deeply controversial, because it was, and Copernicus knew it, right? He was a monk after all. And he knew that this idea of Earth being at the center of the universe had become very ingrained in the Catholic Church, and that depending on who you talk to, his new ideas could be considered heresy, and he can get into a lot of trouble. So Copernicus kept his ideas pretty quiet for a long time. He sent his ideas around to a few people to read, but he didn't publish it widely until he was basically on his deathbed, when he wouldn't face many, if any, consequences. So Copernicus could explain this retrograde motion by decentering the Earth, but there was still the problem of parallax. So remember, parallax is this apparent shift of a foreground object. Right, it's the apparent shift of that tree relative to the mountain as you ride your bike. So Copernicus's whole deal is like, yeah, the sun is going around the sun, right? It is moving. But Copernicus proposed that actually this parallax shift is happening, but that it's way too small to see because the universe is much bigger than we previously thought. So the idea is that if things were much further away, like, right, if these fixed stars were much further away from you, then the shift we would see would actually be much smaller. These fixed stars, as well as the nearby thing you're trying to measure, if all of those were much further away from you, then the shift, so this little shift in angle would be really, really small and be much, much harder to detect. So for Copernicus, this wasn't necessarily a problem for him because he just proposed that the universe is just bigger than we think. His calculations of a sun-centered universe were much better at predicting the locations. So parallax wasn't a problem, retrograde motion wasn't a problem. So you have an assignment this week dealing with parallax in which you'll explore kind of how this works, as well as its limitations. The next contributor we will discuss is Tycho Brahe. So he proposed yet another model of the universe in which the Earth is still in the middle and the moon orbits the Earth. The sun also orbits the Earth, but the other planets orbit the sun. So this is just sort of wrong in kind of a different way, but it settled or calmed some of the controversy that surrounded Copernicus's idea. But again, it's not correct, and this actually isn't Tycho's most important contributions. Um, what his major contributions had to do with were making really, really excellent observations. So he made these great observations and he really honed tools that aided in making these observations. So Tycho was independently wealthy and he really wanted to make the best astronomical data tables that he could. So an important tool that he honed to make these observations that went into these data tables is the quadrant. So this tool allows you to measure angles and allows you to repeat those observations. So this is Tycho right here in this drawing. This gigantic thing is the quadrant. There were smaller handheld versions that we could use, but it's good to have it kind of bolted into the ground so we're not moving around. He was able to make very good observations. So this type of tool allows you, yeah, to measure those angles. And before, people were relying kind of on hand drawings and estimations of where things were in the sky. But with a quadrant, you could be more quantitative about it. You could really repeat your observations, which is very important for a quantitative science. Tycho made some new observations as well. He observed a supernova. So we know now that that's an exploded star, but at the time it was kind of known as a new star that eventually fades away. But he observed one of those. He also observed the path of comets and noted that the orbits were not circular, and in fact crossed the orbital paths of other planets. So this is kind of one of those, early steps away from this idea of, perfect circles, a perfect heavens. Tycho was, by all reports, a big personality. Some people liked him, some people really didn't like him. He lost his nose in a sword fight, like in a duel. So he wore a prosthetic nose for most of his life. Um, his death is also controversial. One story is that he was poisoned. Another story is that he was hosting a large dinner party and didn't want to get up to use the bathroom, so his bladder exploded. That one seems pretty unlikely to me, but people have tried to look into this, and it's still really kind of unclear exactly how he died. But probably Tycho's biggest contribution to astronomy is who he hired as his assistant. So he hired Johannes Kepler, who is a mathematician who became really interested in mapping out the shapes of orbits. Tycho really had the best observations of the day, and Kepler wanted to use them to calculate orbits, but Tycho was a little protective of his, I guess, intellectual property, and he wouldn't give Kepler all the data at once. So there was a little bit of tension there between them. Eventually, though, Tycho does die, as all mortals do, and Kepler gets his hands on all the data. And from this data, he was able to calculate and analyze the orbit of planets and eventually developed his three laws of planetary motion. So these laws are really empirical. He figured them out from observations. So the first of Kepler's laws states that planets move in elliptical orbits with the sun as a focus. So an ellipse is really just kind of a math word for oval. It's what's known as in math as a conic section. So say you have a cone like these on the screen. If you cut a section just straight across and project it down onto a page, you get a circle. But if you cut the cone at kind of more of an angle like this, then you get an oval shape, which is an ellipse. Okay. So here are the examples of a few ellipses. So the squished axis so of these two, of these two right here is squished axis. The squished axis is the minor axis, and the distance between the center, marked here at C, and the edge, so here, that is called the semi-minor axis. The stretched side, so that's kind of the long way, it's called the major axis, and the distance between that center and the edge is the semi-major axis. So we can talk about how ovally an ellipse is by talking about its eccentricity. So eccentricity is the distance between the middle and the focus divided by the distance between the center and the edge. Okay, that is eccentricity. That's how we define how ovally an ellipse is. So eccentricity is measured from 0 to 1. The larger the number, the more eccentric, right? The more ovally. So we have a circle right here. A circle has an eccentricity of 0. It's basically a special case. An ellipse has, rather than just like a center, right? For a circle, we have a center point where everywhere you measure from the center to the edge is the same. It's not true with an ellipse. An ellipse, rather than a center that's kind of important, there are two focuses. So these two points here. So to draw an ellipse, you could like stick some pins in 2 points, attach a string to them, put your pencil in between, and just kind of pull the string taut and use it to go around like this, and you will get an ellipse. So a circle is a special case of an ellipse where the two focuses are kind of right on top of each other. And according to Kepler's laws, which are based on observations in our solar system, the sun has to be at one of these focal points. So we have there, I don't know of any orbits that are perfect circles. They're always squished in some way. And the sun or star that a planet is orbiting is always at one of these focuses. So the only situation in which a planet is always the same distance from the star is this very special situation in which the orbit is a perfect circle. But in other cases, like most cases, there are times when the planet is closer to the star than other times. So let's say in this middle ellipse right here, we have the sun at this F1 focus point. The planet orbiting will be closer to the star here than if it's over here. So this has implications for others of Kepler's law, especially the second law, which says that a planet covers the same area of space in the same amount of time, no matter where it is in its orbit. An alternative way to say that is that a planet does not go the same speed at every point in the orbit. So this is what I mean when I say that that it covers or sweeps the same area of space. So this is a video of, or a GIF of a model of a Keplerian elliptical orbit. The black dot is orbiting the point in space where the lines cross, so right here. So the periwinkle blue wedge is the kind of the area that we're talking about, the area it's sweeping. So watch this video for a second and really see what this means, right? The planet starts out far away from the star. For a bit, the wedges seem to be about the same shape, right? But then, because of the elliptical orbit, the planet comes in closer to the star. The wedge gets shorter and the planet speeds up. To cover the same amount of area in a particular span of time, the planet has to be traveling faster at some points in its orbit than others. This gets more extreme with greater eccentricity. So this is a model orbit of a planet with an orbital eccentricity of 0.2, which is still actually much larger than Earth's eccentricity. But each one of these wedges is the same area. So you'll see a red line, which is where the planet would be if the speed was constant throughout the orbit, right? So like watch what happens. The planet is definitely changing speed, right? So each one of these wedges is the same area. And the red line is the planet if it was a constant speed. And so it's very clear that the planet is not a constant speed through the entire orbit. It's changing speed. It overtakes the red line at points, and the red line overtakes it at some points. Now check out what happens with an eccentricity of 0.8, right? So the bigger the eccentricity, the more ovally. So again, all of these areas within the dotted lines are the same area. So really this just whips around the star right at the end when it's at its closest approach. And it really slows down as it's far away. So I think this is really cool and very satisfying to watch. I could do this all day, but I won't because there is one more law of planetary motion that we need to talk about. It's really arguably maybe the most important one, but the third law of planetary motion is a planet's orbital period is proportional to the size of its orbit. So specifically, the square of the orbital period in years is proportional to the cube of the semi-major axis. So remember, we have an ellipse. The semi-major axis is this elongated axis from the center point to the edge. So this maybe seems like not too big of a deal, but if you have a system of planets like the solar system, this ratio of t squared to a cubed is the same for all planets in this system. It's a relationship between orbital period, or the amount of time it takes to orbit the sun, and the distance from the sun that is shared by all planets in the solar system. You have an assignment that works with Kepler's laws that uses an applet to adjust eccentricity and distance. For that, we use kind of a simplified version of this in which the square of the orbital period is equal to the cube of the semi-major axis. So it just simplified a little bit, but for the solar system, it should work pretty well. You also have an assignment that deals with parallax. You'll be measuring parallax of some objects on your own and using a spreadsheet to calculate the distance. There's a little bit of math this week, but not too much. If you have any problems or questions, please come by my office hours or drop me an email. I'll be happy to help. So good luck. Have fun.